In our course, Geography 15, Violent Weather and Natural Hazards, we now explore Chapter 10, which is all about mid-latitude cyclone storms. Well, what's the latitude of Fresno? You all should know by now. It's about 37 degrees north latitude. So if you look at the globe, and if you, of course, did the first page or so of problem set number 3, you know that we are in the middle latitudes, between 30 degrees and 60 degrees north latitude. The kinds of storms that affect our area in the winter and early spring are called mid-latitude cyclones because, hey, we're in the mid-latitudes. So Chapter 10 is going to cover the polar front theory, where mid-latitude cyclones tend to form, how they tend to develop. We'll talk about something called the Storm of the Century, which was a mid-latitude cyclone on steroids along the east coast of the U.S. in March of 1993. There is an equally infamous mid-latitude cyclone along the west coast of North America, the Columbus Day storm, October 12, 1962, and I'm old enough to remember that, fortunately or unfortunately. Mid-latitude cyclones and their association with Great Plains blizzards. Maybe some of you are writing about blizzards for your major writing topic. And polar lows, which are kind of interesting. They almost look like hurricanes on satellite imagery. So here we go. There was a father and son team, last name Bjerknes, and a guy named Solberg and a guy named Bergeron. And they were up in the Scandinavian area of northwest Europe. And after World War I, they published a paper regarding the movement of air masses. And through this paper, they developed a working model of how a mid-latitude cyclone progresses through stages of birth, growth, and decay. They actually measured temperature and pressure and wind direction and then collated this data and examined it later. And their paper came out in 1921 after World War I was over. Mid-latitude cyclones, they theorized, these storms form and move along what's called the polar front, which is the dividing line between cold polar air to the north and warm subtropical air to the south. And by the way, for this conversation, we will exclusively be dealing with mid-latitude cyclones in the northern hemisphere, because after all, that's where most of us have lived in our lives. There are 6 stages, according to this theory, regarding mid-latitude cyclone development and decay. Initially, the warm air to the south and the cold air to the north are at a stalemate. That's called the stationary front. Then, as warm air advances northward and cold air advances southward, you get a frontal wave. As that wave becomes more intense, it's called an open wave in the 3rd stage. The 4th stage is a mature cyclone. The 5th stage is what we call an advanced occlusion. That's typically when the rain and snow are heaviest. And then the 6th stage is a cutoff cyclone, which means that the storm essentially dissipates. Now I'm going to show you pictures of all 6 of these stages. So here we have the stationary front stage, where the cold air to the north and the warm air to the south are at a stalemate. Secondly is the frontal wave, where cold air plunges southward, warm air advances northward, and you start to get a wave shape on the weather map of this mid-latitude cyclone. The 3rd stage is the open wave. The open warm sector there is where all the warm air comes in from the south. The 4th stage is where the frontal system starts to occlude, where warm and cold fronts come together right near that red L, the low pressure system. That's the initial occlusion. You often get your heaviest precipitation at this stage. The 5th stage is the advanced occlusion. You still can have heavy precipitation, but the system starts to weaken, and by the 6th stage, you have the cutoff cyclone, where the original low-pressure system can be some distance away from a newly developing stationary front, which may again at some point develop into an entirely new mid-latitude cyclone. Here are the 6 stages all together so you can see how they progress. The region of lowest pressure in a mid-latitude cyclone is called the central pressure, and that's at the junction of the 2 fronts, the warm front and the cold front, in the frontal wave and open wave stages. So that's going to be around the 2nd stage and the 3rd stage. The precipitation, which is noted in green in those previous maps, forms in a wide band ahead of the warm front and in a narrower band in association with the cold front. The region of warm air between the warm and cold fronts is called the warm sector. It's that warm, moist air that comes in from the south that tends to fuel the strength of this mid-latitude cyclone. Now, the mid-latitude cyclone storm will start to dissipate in the advanced occlusion stage. The precipitation starts to decrease in intensity. The lowest pressure starts to be not quite as low as it weakens. Because when you get to the advanced occlusion stage, you essentially have cold air on both sides of the front. And so it starts to lose its distinct characteristics. This next frame, the next slide, which is figure 10.2 in your book, shows a family of mid-latitude cyclones as they're draped across the northern hemisphere. This is not at any particular date. It's just a way of giving you an idea of what these may look like on a surface weather map, how meteorologists and their computers draw them. A notorious mid-latitude cyclone follows this mid-latitude cyclone model developed by Bjerknes, Solberg, and Bergeron. Many of you probably are not old enough to remember this, but on November 10th, 1975, the winds associated with this howling mid-latitude cyclone, as it was right over the western part of Lake Superior, were strong enough to topple an iron ore freighter, which was sailing across Lake Superior, called the Edmund Fitzgerald. Regrettably, because I can't exceed 15 minutes of audio on this PowerPoint, I'm not able to show you this movie. But what I would like you to do is to go ahead and when you play this PowerPoint, I want you to engage this YouTube movie, which is actually put to music. There is a famous, still living folk singer from Canada. His name is Gordon Lightfoot. Perhaps some of you know who he is. I think he's recently played the Hanford Fox Theatre. In any case, he wrote a famous song and recorded it, which was a big hit a year later in 1976, about the wreck of the Edmund Fitzgerald. Please take the time to watch this video so you can see how destructive a mid-latitude cyclone can be. Winds on the 10th of November across Lake Superior reached as high as 85 miles an hour, causing large waves to basically break up the Edmund Fitzgerald and cause it to sink in Lake Superior. These are favorite areas in North America where both mid-latitude cyclones form and move. That's the top frame, frame A, and then where mid-latitude anticyclones form and move in the wintertime across North America. Anticyclones are high pressure, remember, and cyclones are low pressure. When mid-latitude cyclones form, the term for that is cyclogenesis or cyclogenesis. Whenever you have a very strong flow of air in the upper levels of the atmosphere, which goes perpendicular to a major mountain range, and that air descends on the leeward side of that mountain range, like the Sierra Nevada or the Rocky Mountains, then all of a sudden, when that air descends to a lower elevation, you have a lot of space above where that air used to move. So that tends to allow for more divergence or separating of air streams in the upper atmosphere, which can cause explosive development of what we call lee-side low-pressure systems, as those strong westerly winds aloft descend on the lee side, or often in North America, the eastern side of a major mountain range, like the Rocky Mountains, or like our nearby Sierra Nevada. Then we have some particularly nasty mid-latitude cyclones which can form along the east coast, which are called nor'easters or northeasters. You have a very warm surge of water in the Gulf of Mexico and the western Atlantic called the Gulf Stream. This enhances the situation because it helps to bring warm, moist air into the open wave sector of the mid-latitude cyclone as it develops. They often will start over the Gulf of Mexico, hug the east coast, so that you have very warm maritime tropical air moving up in the open wave. You have cool, but not bitterly cold, maritime polar air coming in from the Atlantic from east to west. And then, from north to south, behind it all, you have you have continental polar air coming in. So you have a mishmash of three air masses, which can make for a very nasty storm. This is a weather map of a nor'easter storm on the 11th of December in 1992. Then you have the Alberta Clipper, which is the kind of mid-latitude cyclone that can form over eastern Alberta province, Canada, on the lee side of the Rockies. It's a lee side low, just like the one I showed you in the previous slide. Developing mid-latitude cyclones are dependent on the role of upper-level convergence and divergence. Convergence meaning air streams coming together, and divergence meaning air streams pulling apart. For the surface low, the convergence, to rapidly develop into a major storm, upper-level splitting of air streams, meaning divergence, must be greater than the surface convergence of the air. Otherwise, the storm on the surface is not going to develop into a major storm. It'll just be just a plain old low pressure, not doing a lot. Let's go to the anticyclones for a moment, which are also, of course, called high-pressure systems. For a surface high to strengthen, upper level convergence, or coming together of air above your head, has to be strong and exceed low level divergence, or splitting apart of air on the surface. Otherwise, the high or anticyclone that develops on the surface will weaken. So basically, what you want then for a surface high to develop is airstreams rapidly coming together above your head and then slamming down on the surface and then diverging outward. And that's sort of on the right-hand side of this figure 10.6 that you're seeing on the screen. For the surface low pressure to develop rapidly, to intensify, the upper level trough of low pressure pretty much needs to be located just to the west of the surface low. You can see how the upper level purple L is not lined up with the lower level red L. That's what you want in order for the surface red L, or low pressure system on the surface, to have significant convergence or coming together of airstreams to then move upward in response to rapid pulling apart aloft or divergence of airstreams. You can see the diagram goes from the surface up to about 30,000 feet. So the bottom line is convergence on the surface is dependent on divergence aloft, and divergence, or high pressure on the surface, is dependent on convergence aloft. These things all relate to each other. Regions of well-developed convergence and divergence aloft typically occur when well-developed waves exist in the flow aloft. We're talking about the upper atmosphere now. The distance from trough to trough, or from ridge to ridge, just like over the ocean, is called the wavelength. The wavelengths can be many thousands of miles long, and if they are, we call them long waves, or Rossby waves, and that's named after the meteorologist in the 1930s who first quantified this. But there are shorter wavelengths in the upper level flow above your head, and we call these short waves. They can often be embedded in the long wave flow. If meteorologists watch these short waves closely and how they develop, that's the key to figuring out how storms down here on the surface where we are can develop rapidly, because short waves can often excite the flow of air aloft and increase the strength of the long wave circulation and allow a surface storm to develop very, very rapidly. Here is a panel that shows day one, if you will. You can see how long the long wave is looking at the green arrow on the lower part of the graphic. It's a very long wave trough covering all of North America with 3 embedded short waves. Watch how the short waves by day 2 move and strengthen or weaken. So you can compare the two. Once again, I'll go back to day 1. Well, I guess I can't. Well, in any case, you get the idea. If you play those back to back, you'll see what I mean. This figure shows how the flow aloft is extremely a governing factor with how a surface mid-latitude cyclone can develop. In the first panel, panel A, you see a flow of air above your head coming out of the west, pretty much, moving from west to east, and that's where the cold and the warm air are juxtaposed against each other but not making a move against each other. But if you have more troughiness aloft above your head, then you have basically convergence on the western side of the trough, divergence on the eastern side of the trough, and that starts to develop a wave pattern on the surface as the mid-latitude cyclone develops. And then toward the end of the life of the mid-latitude cyclone, you do not have a distinct, sharp, low-pressure trough in the upper atmosphere as the parent low sort of shears away and the winds aloft weaken, and then the storm on the surface starts to occlude, and the whole system tends to weaken then over time. We'll continue to explore mid-latitude cyclones in Chapter 10, Part B.